Hello, in this video, let's talk a little bit about current mirrors. So this is a short video and we'll look at a very important circuit component, the current mirror, and we'll see how that works. So as I mentioned to you before, normally there's one power source in the chip and the current from that power source needs to be replicated across the design and bias the appropriate circuits. Right? For example, you have this reference current Iref and that current needs to be replicated around the circuit. So you need to have a way to sense that current and then to generate a similar current and then use and basically that component basically can be repeated across the circuit. Now we know that a transistor, when it's biased in saturation, I can get the right current from that transistor if I'm able to find out the right voltage it needs to be given, right? So now let's consider a diode-connected transistor. A diode-connected transistor, if I have a current flowing through the diode-connected transistor, then the voltage developed across the gate to source voltage of that diode-connected transistor you see is related to the current that is flowing in this transistor configuration, simply because this configuration is always going to be in saturation. So if I consider this combination here, so I have Iref. Iref is flowing into a diode connected transistor M1 whose gate is also shared with another transistor M2. And let's try and see how is Iout related to Iref. Now this M1 transistor, because Iref is flowing into this M1, it's going to generate a voltage that is going to be dependent on this reference current. And therefore I can write my Iref as IDS1, which is half Kn prime W by L1 into VGS1 minus VTH1 the whole squared. Now if I can ensure M2 is in saturation, how do I ensure that? If I can ensure that its VDS is much larger than its overdrive voltage, then in that case, transistor remains in saturation. I can write my Iout as IDS2 half Kn prime W by L2 into VGS2 minus VTH the whole squared. Now both these transistors share the same gate node, hence the same gate voltage. And if I design them in such a way that the VTs of both the transistors are equal, then what I'm going to get is that the ratio of the reference current to the output current is simply the ratio of the sizes of the two transistors M1 and M2. So as long as I ensure that my M2 transistor is in saturation, right? As long as I ensure that, then basically this pair, and this is known as a current mirror, this M2 M1 pair can be used to move or to set up currents in various branches of a circuit. Now obviously we looked at a very ideal case where there's no channel and modulation. In reality we know that, so ideally your transistor in saturation looks like this, IDS versus VDS, where IDS is roughly independent of VDS. Right? In reality, however, your IDS is not going to be straight, but in fact has a slope. That slope is characterized by this term lambda. And therefore, in reality, you will assume that Iout by Iref is going to be sum 1 plus lambda VDS2 by 1 plus lambda VDS1. That is, this output current is going to be modulated by whatever is the output voltage that is developed across M2. And so ideally now you want to identify a technique by which you can reduce the effect of this output voltage on Iout. So in the ideal case, you want this Iout to be solely determined only by Iref and not by what is connected outside the circuit. So you see that these current sources are very popular, these current mirrors are very popular, and they're used a lot to steer currents in various circuits. For example, here you see that this M1 M2 pair ensures that the current that flows in this in this branch of M3 M2 is going to be some ratio of Iref, and then M3 M4 configuration is going to ensure that whatever current is built in this branch, a ratio of that gets flown into this Iout. Similarly, you have a bigger circuit where you can consider multiple current pairs to bias currents in various branches of the circuit. Now, how do we reduce the dependence of the current on the output voltage? So let's add another transistor on top of the output voltage, right? So if I want to reduce the impact of lambda, one thing I want to do is, can I ensure that this output voltage of VDS, this VDS is the same as this VDS, right? So if I can assume that VDS2 is equal to VDS1, then even if lambda is present, because lambda VDS1 is going to be equal to lambda VDS2, eventually I'll not get a dependence on VDS2. So therefore, that means that I need to find a way by which the output voltage of M2 transistor stays close to the VDS of the first transistor. That I can do by connecting this transistor M3 in such a way that the bias voltage of M3 can be selected in such a way that this VB can be VGS3 plus VDS1. So I can pick the bias voltage of M3 to be in such a way that this Vx remains at VDS1, right? And so therefore what's going to happen in such a case is you're going to have this current which is going to be relatively insensitive to the output voltage. Now again here this configuration of M3, M2 is a cascode configuration. And therefore what you'll see is that this node voltage Vx is going to be held relatively steady because Vb is steady. So Vy can change substantially, but you'll see that Vx is not going to change because Vx is going to be dictated by Vb. And therefore that brings in a lot more stability into Iout. So you see that even though Vy keeps changing, because Iout is going to be determined by this transistor, Iout remains relatively unstable or relatively stable compared to the voltage Vy. And if I want to again ascertain what is the minimum value of Vy, I need to ensure Vy is large enough that it supports both these transistors in saturation, which means Vy cannot go below the sum of VOV3 and VOV2. Now one way to generate this essentially is use what is known as a cascode mirror, and the way we would do that is we'd connect another diode-connected resistor here, transistor here, M4, and ratio them in such a way that the ratio of M3 to M4 is the same as the ratio of M2 to M1, right? And so in that case, when you don't assume any body effect, what's going to happen is VGS2 is going to be equal to VGS1, right? And VGS1 is always going to be in saturation. Similarly, VGS4 plus VGS1 is going to be the same as VGS3 plus VGS1 or VGS2, right? And so therefore we set it up in such a way that this node here is going to be the sum of two VOVs. And now in this case, however, you need to ensure that your output voltage swing is going to be slightly smaller than the previous case. That is because here the output node has to be in such a way that we need to ensure both M3 and M2 are in saturation, which means that this node has to be at least a VT higher than this node, right? And therefore that means that VD3 minimum is going to be VOV1 or VOV2 plus VOV3 plus a VTH, right? And so therefore you see that in such a case of a cascode mirror whites generally allows us much more stability than the previous case. You'll see that it's going to come at a cost, and that cost is given by a slightly reduced output voltage swing. So this is a very short video on mirrors and how they are used. We'll see later on how these mirrors keep appearing in all circuits, and hence understanding how mirrors work is critical to understanding analog circuits.